Hello. In this tutorial, we will be using machine learning to train a distribution on discrete random variables on a dataset so that we can use the model to generate variations on the melodies and phrases that are present in the dataset. To do this, we first open up the model that we've created in the last tutorial. If you want to keep the original model with the factors around for later reference, you can now duplicate this asset and create a new one for the machine learning tutorial. Here we have created some factors to model our distribution by hand. Now we will delete those factors and instead have the distribution be trained by data, so that we don't have to worry about all of this ourselves. Both approaches are valid, and sometimes you will like to use a mixture of machine learning and hand-designed factors. But now let's focus on the machine learning part. Before we can do any machine learning, we need data. To get the data into Unreal and use it with Concord, there are a million different ways. Basically, you can have a JSON file with values in it that you load as an asset into Unreal as a Concord crate, and then you can observe it in a model. But in this case, we will use Concord itself to generate our data. You can also use MIDI import functionality of Concord to create data from your MIDI files, so you can use a sequencer to generate your data. But as I said, today we will be using Concord itself to generate a very, very small dataset. But since our problem is quite manageable and it's not a very large neural network to train, we can actually use very small datasets and then get very targeted new samples from the trained distribution as variations of our dataset. In our case, a dataset is a collection of Concord crates that contain observations for the random variable boxes in our model. So we're looking for 8 values for our progression and 32 values for our melody, and those values are in a space between 0 and 15, which is interpreted as scale degrees. So let's build some different crates just using Concord nodes. For example, I can use a repeat node to repeat the scale degree 8 for 6 times, and then I can duplicate this and repeat the scale degree 6 2 times. Then I can just select the 2 nodes and create a concat node by right-clicking anywhere in the space or hitting tab, which will automatically concatenate them, and then I'll just route them to an output. Names in Concord are unique, so in order for this output to be called progression, I will need to temporarily rename this progression box up here, simply by adding an underscore, for example, and then I can name this progression. We have an output here. If we want to audition this progression, I can also just use our phrase that we have set up here. And then we can take a listen. So it's very simple, but for the purposes of this tutorial, it will be useful. We will also create a melody just using some nodes. For this, I will first chuck in a parameter of integer type, call this melody base. And I will just add 8 values to the default array. And I already know kind of a melody in my head just using scale degrees that I can just type in here, going from 1 to 5 to 8 to 12, back to 5 up to 9, then back to 5 up to 10. And then I will just repeat this 3 times. And for the last time, I'll have a bit of a variation in this melody base, so I can use a set node to set the last value in this parameter by specifying -1 here at the index. And I'll set it to 8, because here it is 10. For the last time, it'll be 8. Once again, I will concatenate these two, and then I'll just put these into a melody output. Let's hook this up to our preview setup here and take a listen. Okay, I'm happy with this melody and progression, and I want to save it as a data point in our dataset. I can simply select the outputs that I want to save and click Selected Outputs to create. Then I will just create a new folder here and call this my dataset. And inside I will save this as phrase 1 and save. I will create one more phrase, so we have some proper machine learning, not just with a single item in the dataset, but at least more than one. For this, I will just kind of change up the chord progression a little bit. Let's say 1, 6, 4, 5. And let's have each one just repeated twice. And then we can just select all of them. Once again, type concat, and we'll get a bigger concat node. Can pipe that into the output and also into the preview. Now for the melody, I will simply change up these the melody base a little bit. Let's say 12, 10, 9, 12, 10, 8, 7, 8. Or let's use the 6th scale degree, which will fit in a couple more contexts. And then we'll just, once again, have some variations on this. For example, by setting index 4 to 13 and having these two alternate. So we will once again just concat these and then repeat this twice. Let's see what we have. Alright, I'm happy with this. I will once again select my outputs and then just save this as phrase 2. Now that we've created our dataset, we can go on to deleting our generative nodes down here and just plugging in the boxes back again. I will also make sure to rename these back to progression and melody, so that when we observe the crates, these boxes get their values set correctly. We can actually have a look into the dataset folder. If we look into a phrase right here, we have these integer blocks where we have values for progression and values for melody, which got saved from our model. Now we will take a hidden Markov model approach to machine learning here, where we have a hidden box of random variables that stores information about what is currently observed and what will come next. The hidden box will correspond to the hidden knowledge of the model of what comes next in the phrase. And we will use a box of size 8. So let's drop this in, call it hidden, and enter size 8. The state count of the hidden box is interesting. This kind of represents the power of our model. If the state count is very large, the model can learn a lot, and it will basically perfectly learn our little dataset. If the state count is very low, the model will have to make some compromises because it cannot memorize all of the phrase information that is in the dataset, and thus it will have to mix and match, and it'll be less deterministic. So this is a creative setting that we can do here. If I set it up to 100, the model will perfectly learn our two dataset entries. But if I set it to something low, like 10, the model will have to make some ambiguous decisions on the values for the hidden states and also for the observations. To set up our hidden Markov model, we can simply create an emission node. This is a special factor with a hidden and observed input where we connect boxes. So we can connect our hidden box to the hidden pin on the emission node, and then we can emit into the progression box. We will also emit from the hidden node into the melody box. This works because, once again, the shapes are compatible, and every single random variable in the hidden box will emit 4 random variables in the melody box, 4 consecutive ones. With this setup, we can now start creating samples, but since these emission factors have not been trained, this is just a uniform distribution. To train these emission factors, we can use the Learner tab or Learning tab here in the Details window. First, we will have to choose a learner. To train hidden Markov models, we want to use the Baum-Welch algorithm, which is specially suited for this problem and is very efficient. And we get a bunch of options. For us, we just want to set the dataset for now, and this can be a relative path. So we have our model right here, and our dataset is right here. So we can just enter dataset in the dataset directory. The created learned parameters will be saved in a crate of the name right here. And we have some options for concurrency and also how many updates will actually be done, and some updates for some settings for convergence. But right now we'll just click learn. And we see here the progress is almost instantaneous, and in the log we can see how the loss went down from a fairly high value of 120 for the random initial setting all the way down to 6 after the training was completed. If I let the training run for more updates, it will become even better, even though we have very little states. However, early stopping can also be used as a way to let the model be a bit more ambiguous and have a bit more breadth of the available outputs. If I want to check out the effect of the training, I can simply load up the learned parameters, which will then affect these emission node factors. To do this, I can add another default crate to the model. These crates will be set whenever we sample a new variation, and they can either observe boxes or set parameters, and the emission node contains parameters for all of these probabilities. So I'll just pull up the learned parameters here by typing learned and then navigating to the one that we just trained, which is in our basic game folder. And now if I press the spacebar, the model becomes quite sure of what it is supposed to do. We get a sequence of hidden values that then emit a sequence of progression and melody values. Let's take a listen to the sample. So this sample was not in our dataset, but it is quite close to the 2 samples that were in the dataset. Let's try another one. So if you remember, or if you want to go back to the part of the video where we created this basic sample that this is a variation of, it is actually quite close. However, there are a couple of changes, and in the chord progression especially, we can see there is some instability here between the 2 scale degrees that are present in the original sample. However, this instability is not necessarily a bad thing, since it constitutes a variation of the original one, and in a setting where we always want new and fresh ideas, this is actually kind of cool. Alright, in the next tutorial we will be looking at how we can apply our models in a real-time setting and actually have them interact with player input. Thanks, bye!